For this lesson, we're going to look at how we can represent relationships between two quantities. So like it says in the beginning, for relations, much of mathematics involves a search for patterns and relationships between various sets of data. Many real-life applications of mathematics investigate relationships between two quantities. For example, the value of a computer or any electronic device related to its age. The price of a watermelon is related to its weight. The time taken for a person to walk to school is related to the distance that has to be walked. In math, the comparison between any two sets of elements is always called a relation. Now, there's literally infinite possibilities for examples of relation. We could say the amount of money an employee makes related to hours worked. But there are literally infinite examples we could use. When we're representing the relationship between two quantities, there's a number of ways we can do this. Some of them are ones that you should have encountered in the past. So we can represent them in words. We can represent them as a table of values. We can represent them as ordered pairs. We can represent them as an equation, and we can represent them as a graph. These are all ones that we haven't only encountered before. We did in the last lesson. There's a couple of new ones you may have never encountered before: a mapping or arrow diagram, and in function notation. Not all relations can be represented in function notation, but we're going to get into greater detail for that later. So, if you consider a specific example, the cost in cents per kilometer of a car is related, as driving a car is related to the speed s kilometers per hour at which it is driven. We will use this relation to introduce some ideas which will develop throughout the course of this unit. So the example illustrates a relation between two variables. The variables are c and s, which we can find in here where it states what variables or what letters are going to represent our two sets of values. C is considered the dependent variable because the cost is dependent on the speed in this case, which means that S we're going to call the independent variable. Another way that we can relate these is we can call them the input, which would be our independent variable, versus our output, which is our dependent variable. Now, the input values, so every different value we can put or do put in to the input makes up the domain. Oh, sorry, get the colors proper. Makes up the domain. The output is going to be the range. So there's a number of different things we have here. We call it the independent and dependent variable. So what variable are we going to use on our graph, on our chart, or whatever to represent this data? We have the independent is our input, what values we're putting in, and the output is going to be our dependent. That's what values come out after we do the process. Every single set of values, so all the values that we input are the domain. Every values that we get for output are the range. These are going to be some of the most important terms you're going to use going forward, especially domain and range. That makes up a big portion of our future math courses. So, obviously we'd not be able to collect data for every possible input. So we suppose that we're going to choose specific ones. 20, 30, 40, 50, 60, 70, 80, 90, all the way up to 120 kilometers per hour. The diagrams show how the information can be represented in different ways. So if I'm doing it as a table of values, the table can be vertical or horizontal. In this case, I used a vertical table. And we can see that here we have our output, if it's vertical, is always on the right, and our input is always on the left. If we're doing ordered pairs, input on the left, output on the right, just like with our previous case. If I'm doing the mapping notation, I have my input on the left, I have my output on the right. If I'm doing a graph, and we've already experienced this, my input is the horizontal, my output is the vertical. Now, one thing you will see here is that the mapping diagram looks very similar to the table of values to begin with. The biggest difference with our mapping or arrow diagram is that we can see that, unlike with the table of values, all of the values for our output are done numerically or alphabetically on the right, and we don't repeat values. So we can see here that there are some repeated values. We can see that there was a 7.6 and a 7.6, that there was a 7.9 and a 7.9. So we only list them once, but then we take the input values that link to it and then draw a line connecting them to state these are the two input values that would relate to that one output value. Because we have only chosen some of the possible input values, it's obvious that an output value could have been determined for any input value greater than 0 up to the maximum speed of the car. So it makes sense to connect the points on the graph because all the values are going to be continuous. We know that the speed is going to be continuous. We know that the cost is going to be continuous. They're going to both change gradually. So if I have a graph for a different equation, in this case, our graph is not linear, it's going to be quadratic, where we said that c is equal to 0.001 s squared minus 0.14 s plus 12.4, then when I'm doing it graphically, then it's going to come down like this. It's going to come up, and I'm going to connect all those points. Now, we can't have the speed be 5,000 because there's no way that the car is going 5,000 kilometers per hour. So if we were to do this properly, we'd need to know, well, I mean, one, we know that eventually it would hit a point of when the speed is 0, but on the other side, we're going to have a maximum. We don't know the maximum of the car is 120. We just stopped at 120. But it's likely that this would keep going a little bit longer. Now, when we're talking about the independent and dependent variables in a relation, the values of the independent variable represent the inputs, which we already know, and the corresponding dependent variables are the outputs. Independent inputs, it's easy because it's an in and an in. Dependent outputs. In an ordered pair, the values are the first coordinate is the independent, the second is the dependent. In a table, it's whichever value is given first, whether on the left or on the top, is going to be the independent, and the second one's going to be the dependent. In a mapping diagram, the arrows always go from the independent to the dependent. On a graph, the independent is horizontal and the dependent is the vertical. In an equation, we isolate the dependent. which means that the dependent in an equation is going to be by itself on one side, and all the processes that are occurring are happening to the independent. So I'd be, like in this case, saying that I'm taking my independent value, I'm multiplying it by 3, and then I'm subtracting 5 in order to solve what the dependent value would be. So, if I am putting this in practice, it says the diagrams show relations expressed in different ways. In each case, first state the independent variable, then state the dependent variable, list the inputs, and then list the outputs. So if I'm going to apply this, then I'm going to say that for the first one, the independent variable is the one on the left, which is going to be P. The dependent variable is on the right, so the dependent variable is going to be Q. The inputs are the 3 values here, which are 4, 10, looking at the wrong one, which are 5, 8, and 11 right here. And the outputs are over here. They are 10 and 16. For example B, the input is V. The output is A. Listing the inputs, I have 4, 10, and 25. Listing the outputs, there's some repeated, so I'm only going to list numerically the different ones. They're 12 and 15. Getting to example C, the independent is going to be on the left, represented by B. The dependent is going to be on the right, represented by a lowercase c. The independent variables, or the inputs, are the values on the left, three, 4, 5, and 6. And the dependent variables are on the right. Seven, 11, 15, and 19.